Hi class. In this video we will expand the concept of torque and get us to a point where we can start solving problems. And I want you to consider a door. So here you have the wall and you have a wooden door attached to this wall. And this wooden door rotates around this point, which means that it can rotate either this way or it can rotate this way, right? Now, intuitively, you know that if you would like to open this door, you can actually apply a force to it. So you can apply a force to it right here, and the door will open. But as we discussed before, if you apply this force here, at this point in this door, it will cause this door to rotate this way, meaning that its rotational state of motion has changed. If that's true, then that means that this force induced some angular acceleration. And we know from our previous video that torque is the analog of force as far as rotational motion is concerned, equals the moment of inertia times the angular acceleration. So this already shows you that a force can indeed induce a torque on an object that's free to move around a point. Great. Now let's consider a couple of other things. Now imagine that you take the same force here and you apply it closer to the hinge. Right there. Now, what do you think is going to happen? Is this door going to open like it did here, or will it open slightly at a slower rate? And this isn't, I'm saying slower rate in a colloquial term, as in you will be able, would you be able to tell the difference? Moreover, if you wanted to make the door open as fast as it did when you apply this force at the edge of the edge of the door, what do you suppose this force here would need to be? Bigger or smaller? Another question. What if you were to exert a force right at the hinge? Let's say there was another wall here and you mistakenly thought that the door opened this way. Would the door open? So there's a force here, same force, right? Same force. And finally, suppose that you were able to somehow apply a force this way, same force. Would the rotational motion of this door change? As in, if you apply this force over here, parallel to it, would the door swing right or left? Okay, so this is something you can probably try in your own apartment or home or whatever you are located at this point. And I can tell you that a force applied at the point of rotation will not cause the object's rotational motion to change. In other words, the door will not rotate. If this force is also applied in this way, the door will not rotate. And here, the door will rotate pretty quickly. And here, the door will probably also rotate, but not as quickly. And I'm using the word quickly colloquially here. So that tells you something. That tells you a few things, actually. It tells you that whenever I want to induce a torque here, two things matter. One, the direction of the force matters. So if you're at this point right here, you're applying this force going up, and the door rotates like it's normal. But if you apply this force to the left, all of a sudden there's no rotation. And also, the distance in between the center of rotation and where the force is applied is also important, which means that there was quote unquote less rotation if you applied at a distance, a small distance r1 here, than if you would have applied at the distance r2 here. Moreover, if the distance in between the point of rotation and the point in which you apply the force is 0, then there is 0 torque. Okay, so based on these logical arguments, I will expand this equation to also be equal to r vector cross f. Now, the last time you saw an operation with two vectors was work. So work was force times some distance vector. And this turned out to be force times distance times cosine of the angle, where this angle is the angle between these two arrows, right? So here something similar is going to happen. So let's look at what happens here. So let me copy this down. So torque equals to R cross F. Now note that here we had a dot here and a number came out. So if a number came out, I can just set this equals to that. Okay. Here a vector comes out. And there's two vectors. There's an operation vector comes out the other end. So let's go ahead and determine what this is. So let me write the r vector. So let's say the r vector. Now what is the r vector? The r vector is the arrow that you can draw from the point of rotation to where you apply the force. So let's say you apply the force right here, and the point of rotation is that one. The distance in between these 2 points, that's this r vector right here, the arrow. Okay. And now I'm going to use light blue here for the force. So now the force, let's say it can point in whichever direction, but I'm going to draw this vector like right here, right? Because it's a vector, you know you can move vectors around. And usually this force here is being applied at the tip, right? So it's usually right there, but I'm going to move it to the base to show you what I'm going to do, okay? Now, if you remember, with the dot operation for the work here, the dot operation just meant that whatever component of force points in the same direction as D, you take that one and you multiply them together, and that's why you get a cosine of the angle. Here what's going to happen is you have a component that it points along the r direction, right? So you have this component of F that points along the r direction, but you also have this other component that points completely perpendicular to r. I'm going to call this F perpendicular, okay? Now, this F perpendicular is what you multiply r by. So now we're going to start talking about numbers. If I take this length here and you multiply by the entire length over here, you get a number. So you no longer get a vector. So let me take care of that. So remember, torque, this is now just a number. But as we adopted early in the course, I'm not going to draw the absolute bars with this. If I just draw a torque, you know that this is a number now. It's no longer a vector, okay? This will be equal to the distance r times this component right there. So this is this F perpendicular, which means it's whatever the perpendicular component of this r vector here is. Meaning you take the direction of r, which is the direction from the point of rotation to where you're applying the force. Then you compare it to the F vector, whatever component of the f vector that's perfectly perpendicular to the direction of r, that's why you multiply. So you're multiplying this with this. Now, if you note, there's an angle here, theta, and it just so happens that the opposite to this angle right here is a sine function. Moreover, what you can say is that r times f times the sine of this angle is the amount of torque you have, right? This does not account for it being a vector. So let's deal with this vector quantity here. If you have a torque, so torques vectors. How you figured to get out of this vector format is if the torque causes the object to rotate this way, we're going to call this positive, and if the torque is trying to get the object to rotate this way, we're going to call it negative. In the same way that if you had a force problem in one direction, so if you had a force problem in one direction, you usually call this the plus direction and this the minus direction. So we're going to, so since we're in this class, we never will do three-dimensional problems. We will never do two-dimensional problems or three-dimensional problems. We will only do two-dimensional problems, which means that the torque can only be positive or negative. Right here for two-dimensional problems, which is the entire scope of this class anyway. All right, so let's add another layer to this. So resuming what we just talked about in the previous board up there, torque is the moment of inertia times angular speed, which can also be expressed by r cross f. And the amount of torque here, to get rid of this pesky cross product, what you do is it's the distance from the pivot to the point in which the force acts multiplied by force multiplied by the sine of the angle. And note that sine of 90 degrees is 1, which means that if your r vector is this way and your f vector is this way, you just multiply them together because the angle here is 90 degrees. Okay, so good, rid of that. All right, so the last thing is let's set up another door. Wooden door here. Again, it is allowed to rotate around the point. It is allowed to rotate around this point. Now let's say that you are trying to open a door and you press with some force F. And but your little brother or little sister or some child tries to play a joke on you and tries to force the door to not open, which means that this other person comes over here and applies a force F. Now let me change that real quick to make it more clear. Let me choose this one. Okay, there you go. Right. So what happens is this here, let's look at our sign convention, right? So F is trying to rotate this door this way, which is trying to induce, it's putting a positive torque on this door. And green over here is trying to get the door to rotate the other way. So it's trying to rotate this other way, it's negative, right? So how do we decide how is this door going to behave? You might think that whoever has the greater force here wins, but that is not quite true. Let's say if what do you think would happen if the forces were the same? So if the forces are the same, it's very it should be you should see that whoever is pushing at the boundary here is going to get the door to rotate this way, right? So if this force is equal to that force, this door is going to rotate this way. And the reason is that in the same way that if you had so a couple of weeks ago, if you had a mass m and you had the two forces, you had force 1 here and you had force 2 here. If you wanted to know if this object was going to go right or left, you had to compare F1 and F2. Whatever force was greater was going to get the state of motion of this object to go that way. Now here, what you're going to do is you're going to compare torque 1 to torque 2 and see which one's going to win. In this case, if force blue is the same as force green, then the torque green here is greater, because remember, torque has this r this distance term in here, okay? And the distance for r, I'm going to put subscripts here. I already picked 1 for blue. I already picked 2 for green. So R2 here, do you see that? Is greater than R1. Which means that this number is the same, F1, F2 is the same, R2 is bigger than R1, which means that torque 2 here is going to be greater. Hence, we get at the final statement for torques and rotational acceleration, which means that once you're looking at the changing rotational motion of an object, you can't just pick a single torque. In the same way that if you want to know the change in the translational motion of an object, you cannot just pick one force. You have to look at the forces all together, which means that if your body is allowed to rotate, the sum of all the torques is what tells you what this angular speed is. So, or this angular acceleration will be. And the angular acceleration is what changes the rotational motion state of the object that is allowed to move. Okay. Now, we also had the good old-fashioned sum of all forces, which you all know needs to be equals to mass times acceleration. As in, if you want to know the change in the translational motion of an object, you needed to account for all the forces acting on such object. And finally, what if I wanted to know precisely what these forces need to be and these distances need to be so that this door does not move? What does not motion mean? Or better, what does it mean for the rotational motion state of an object to not change? If the rotational motion of an object does not change, it means that angular speed is a constant. In the same way that for forces, if the state of translational motion does not change, then the speed, the linear speed here is constant. And you know what happens here. This is called equilibrium. So this is called here equilibrium. This is called equilibrium. And for the casing forces, you all know what this means. If the velocity is constant, the acceleration is 0. So for a object to be in equilibrium as far as its translational motion, the sum of all the forces needs to be equal to 0. And now we arrive at what does it mean for an object's rotational motion to be in equilibrium. It means that its angular speed is constant, which means that its angular acceleration is 0, so that the summation of all the torques needs to be equal to 0. So to answer the question, what happens here is, if we do this really quickly, R1 and R2, F1 and F2, to figure out what configuration of these variables you need to have, you need to compute all of the torques, and if the torque due to person 1 is the same as the torque due to person 2, then this door will not move if it is not currently moving. But another point is that if this is an object that had some constant angular speed, these forces would then cause the object's angular speed to not change in this context. But that is very rare. I think in this course, the thing that we are going to be more concerned with is the new equilibrium condition. This is the new equilibrium condition, in which an object is now, so if you had some sort of object now, it could be anything. It could be some object here, M. If M is allowed to translate up or down, or is allowed to rotate, either this way plus or this way minus around some rotation axis, then the full equilibrium condition is the sum of all forces equals to 0 and the sum of all torques equals to 0. So before you had in two dimensions, forces leads you to two equations, and we use this over and over again in x and y equations. But now the torques will also offer you, in this case, one equation. Because again, in 2 dimensions, torques can be either positive or negative. It's almost like doing forces or kinematics in 1 dimension. So what this allows you is that for the additional degree of freedom, we will also have an additional equation to be able to solve problems. And in the next video, I will be solving one of these new equilibrium problems for you. Have a good day, and I'll talk to you also.